It could be a while before we're comfortable letting machines take the wheel, but autonomous vehicle technology is rapidly becoming as good or better than we are at keeping an eye on the road. Come for a spin this month on Light Matters. This is Light Matters for January 13th, 2016. I'm your host, James Lowe. On this month's show, we'll see how a smartphone app could help cars drive themselves. We'll also check out some of the latest efforts to integrate optical technologies with electronics for computing, communications, and more. But first, we'll take a look at some novel methods for imaging and learning about the brain. One microscopy technique combined with silver and gold nanoparticles could aid the long-term study of brain development and disease. Researchers at the University of Minnesota and Agnes Scott College in Georgia have used laser spectral confocal microscopy to visualize neurons in 3D. The technique is typically used for fluorescence imaging, but when tissue samples are prepared with precious metals, it enables another mode of imaging altogether. The process involves exciting the nanoparticles with yellow and red light to induce plasmon resonances, which produce strong optical signal and don't cause photobleaching. Samples tagged with silver and gold should retain their high image quality for a century or more, allowing for archiving. On a shorter time scale, the technique could be used to monitor the progression of cancer or to track small structural changes in neurons that are often indicators of brain development and disorders. Next up, senior editor Justine Murphy tells us how studying one of the simplest minds in the animal kingdom could advance our understanding of the brain.
A fluorescence microscopy technique has yielded 3D footage of brain activity in wiggling worms, offering insight into how populations of neurons generate animal behavior. Researchers at Princeton University studied nematodes, which are 1 millimeter long and whose entire nervous system contains just 302 neurons. The team found that multiple neurons showed significant correlations with forward, backward, and turning movement. They used a spinning disc confocal microscope with a suite of 3 cameras to capture 3D volumetric fluorescent images of neurons 6 times per second, and to monitor the worm's position and orientation. Custom software tracked the position of the worm's head in 3 dimensions in real time, while a motorized stage and objective kept it within the field of view. The technique could reveal information about how neural networks function in more complex organisms, the researcher said, leading to a better understanding of the brain as a whole. And now back to James Lowe for a look at a camera with street smarts.
Thanks, Justine. Adept at identifying roads, buildings, pedestrians, and more, computational imaging software developed for use with smartphones could form the basis of an autonomous vehicle navigation system. Called SegNet, the app can't yet control a driverless car. But the ability to help imaging devices accurately identify what they're looking at is a vital part of developing autonomous vehicles and robotics, as well as collision warning systems. That's according to researchers at the University of Cambridge in England who developed the software. SegNet sorts images in any object into 12 categories, such as roads, signs, buildings, pedestrians, and cyclists, in real time. The developers said it labels more than 90% of pixels accurately. Much work on autonomous vehicle systems is focused on laser and radar-based sensors, which the Cambridge team said are more expensive and less accurate in real time. Meanwhile, a second mobile app developed by the same team can be used to determine the user's location and orientation from a single color image of a busy urban scene. Now to shift gears, Justine Murphy has this update on efforts to bring optical technologies together with electronics.
Made from silicon using conventional fabrication methods, a microprocessor that integrates multiple photonic components is said to be the first to communicate directly with other devices using light. The device consists of 2 processor cores with more than 70 million transistors and 850 photonic components on a 3x6 millimeter chip. It was fabricated in a foundry that mass produces computer chips, indicating that the design could be scaled up for commercial production. It was developed by researchers from UC Berkeley, MIT, and the University of Colorado Boulder. They said the chip marks the next step in the evolution of fiber optic communications technology by integrating photonic interconnects into a microprocessor. The device uses a relatively small amount of electricity and demonstrated a bandwidth density of 300 gigabits per second per square millimeter, which is about 10 to 50 times greater than packaged electronic microprocessors on the market today.
To learn more about photonic integration, We invite you to join a Photonics Media webinar on Thursday, January 28th. Douglas Gill of IBM will discuss the development of the company's monolithic nanophotonic CMOS technology for short-reach optical transceivers. You can find that and more about silicon photonics this month at photonics.com. And don't forget to check out the January issue of Photonics Spectra, where you can get up to date on the latest trends in education, safety and security, space exploration, and more. You can also read all about the finalists for the 2016 Prism Awards for Photonics Innovation. You can read and subscribe at our website. Join us for our next episode, February 24th, when we'll catch up with some Prism Award winners and bring you the highlights from Photonics West. Thanks for watching. See you next time.